Hello students, welcome to the world of chemistry. This is Dr. Vikram Panchal and I am dealing with wave mechanics for chemistry. And in this chapter, this is lecture number 6. In this chapter, I will explain you Schrodinger's wave equation. For that, let us consider one condition, that this is one and one string is tightly attached to this and it is held tightly. Now, after holding this string tightly, if you tap this string, then it will produce vibrations. And therefore, the string will vibrate in this manner. And these vibrations is because of the oscillations of particles of string, and this will produce a wave. This oscillation is known as simple harmonic motion. Okay, and this is amplitude A. Well, this point is having radial value pi by 2. Here this is pi. This radial value is 3 pi by 2, and here we have 2 pi. So the distance traveled by particle up to 2 pi will be equals to wavelength lambda, because it is one cycle of crest and trough. Okay, so for this type of motions of string particles, Hamilton proposed a equation, and that we have to derive by displacement. So for this displacement y is equal to, we have very common equation, a sine omega t plus phi, where a is amplitude of wave, then omega will be angular frequency, t is equal to time, and phi will be initial phase. So phi is equal to initial phase. That means when particle is here, the initial phase will be 0. So here phi is equal to 0, and therefore we get this formula, y is equal to a sine omega t. Okay, and we can use this one. But before that, what is displacement basically, that we have to find out. So when particle is here at this point, well, at origin, when particle is at origin, the phase difference will be 0. That is why phi is equal to 0. But when particle reach to this level at this amplitude, then the phase difference, because it will be less than this much, is about pi by 2. When particle reach to this level, the phase difference is pi. When particle reach to this point, the phase difference will be 3 pi by 2. And when particle will reach here, the phase difference will be lambda, that is 2 pi. So, at lambda distance, the phase difference appear, which is 2 pi. Then at any distance x, what will be the phase difference? At lambda, if phase difference is 2 pi, then at x, the phase difference would be 2 pi upon lambda into x. If we write this is equal to kx, then k is a constant which is equal to 2 pi upon lambda. Okay. Now displacement of particle on this wave is with respect to time. So if we select few definite times like T1, T2, T3, then we will get set of positions of particle. Barabar? So here this will have position. Suppose at T1 time, position of particle is say x1. Obviously this is wave, and in this wave, particle continuously move from one end to another, and that is why the position will change it. And if it is T2, the position may be x2. If it is T3, let us take x3. That means one time has relation with one position. So one time and one position. So here we can say time and positions are interrelated, and it is 1-1 relation. Therefore, displacement of particle y is equal to function of x. So we write fx. Okay. So now the formula will be y is equal to fx. Now particle is at not origin but at any point x. Then fx is equal to a sine omega t minus kx. We put negative sign because it is a difference and kx is a phase difference. Okay. So to show that it is a negative sign or less than origin, so we write minus sign over here. So phase difference will be minus kx. So this is the formula. Fx is equal to a sine omega t minus kx. Now we have to differentiate this formula with reference to x. So when we differentiate this formula, the above formula with reference to x, then it will be dfx upon dx, okay, is equal to a is a constant, so it remain a. The differentiation of sine become cos, so it is a cos. Omega t is constant, so it remain as it is. X is variable and the constant of variable x is k minus k, so it is minus k, multiplication in minus k. We will keep this k outside of this, so we write minus ka cos omega t minus kx. Okay, so this is dfx upon dx. We carry second time derivation of this one. So d square fx upon dx square is equal to minus ka cos becomes sine. This is constant, so it will be omega t only, minus kx into minus k. Okay, so here we have minus k, so we will write d square fx upon dx square is equal to minus k square a sine omega t minus kx. Okay, so this will remain minus because we have 3 times negative sign, and that is sorry, here it should be minus ka. Okay, so it will be minus a cos omega t, and that is why we write minus k square a sine omega t minus k. Okay, now for electron, as we assume that if we apply this equation to electron, sorry, before that we can simplify this equation. So we can write for electron later on, but first of all we can simplify this equation for it. For instead of a sine omega t minus kx, we write fx. So d square fx upon dx square is equal to minus k square fx. Now we put the value of k. So d square fx upon dx square is equal to minus 4 pi square upon lambda square fx. So this formula was derived by Hamilton for any particle which is moving like a wave, or if it is having wavy nature. Now we know that electron also having wavy nature, so we apply this equation for electron, and as electron is a specific particle, therefore Schrodinger used a new function for electron. Instead of fx, he used Greek alphabet C. Original Greeks pronounce this as psi, we also pronounce this as psi. But it is basically wave function. And for that, we write del square psi upon dx square is equal to minus 4 pi square upon lambda square psi. X component, if electron is moving in x direction. Okay, for x component, this is equation 1. Second, d square psi upon dy square. If electron is going in y direction, we have this formula, minus 4 pi square upon lambda square psi into y factor. And similarly, d square psi upon dz square, if electron is going in with the z direction, is equal to minus 4 pi square upon lambda square into psi z. This is equation 3. Now when we combine all these three equations, then we can have three-dimensional equation, and for that we write partial derivation, and that is del square psi upon del x square plus del square psi upon del y square plus del square psi upon del z square is equal to minus 4 pi square upon lambda square, three-dimensional function x, y, z. Or del square psi upon del x square plus del square psi upon del y square plus del square psi upon del z square plus 4 pi square upon lambda square psi x, y, z is equal to 0. Now here we have lambda. So according to Broglie's equation, lambda is equal to h upon mv. So lambda is equal to h upon mv. So lambda square will be h square upon m square v square. Substitute this. So del square psi upon del x square plus del square psi upon del y square plus del square psi upon del z square plus 4 pi square m square v square upon s square is equal into psi x, y, z is equal to 0. Now, total energy is equal to potential energy plus kinetic energy. Okay, so we put the different equations. So E is equal to V plus half mv square. And therefore, we can have 2 into m into E minus V is equal to m square v square. Substitute this value in this equation. So final value will be del square psi upon del x square plus del square psi upon del y square plus del square psi upon del z square plus 8 pi square m upon h square E minus V psi is equal to 0. And this equation is known as Schrodinger's wave equation. So this way we have derived Schrodinger's wave equation. So in this lecture, this is enough for you. Thank you.